Hello everyone, my name is Akihiro Fukuhara from Keio University, Japan. I'd like to make a presentation about FPGA context-based live migration maintaining network consistency. Based on the development and increasing of IoT devices, many innovative services have been proposed and introduced. For realizing such services, various computing environments have been used to fulfill the requirements of the services, such as latency, network bandwidth, and computation load. More specifically, clouds have many computational resources and are separated from IoT devices. They are suitable for heavy load and delay-insensitive services. In contrast, edges are more suitable for lightweight and delay-sensitive services because they have fewer computational resources and are closer to IoT devices. It is required to combine their computing environments for realizing a comprehensive services, such as services of a smart city, which consists of various scales of IoT services. Since FPGA can realize some applications at lower power consumption, lower latency, and high throughput, FPGA applications have been widely used recently. For example, acceleration and low power solution in a data center, network application, and data anonymization. Next, I will explain the problems of achieving comprehensive IoT services. The first problem is service requests for each computing node change dynamically based on various factors, such as changes in the number of end devices in a system or changes in users' behavior. Resource limitation is also a problem. In particular, edge environments have less computational resources than cloud. There is no room, there is no room for dedicated nodes for each service at each location. Finally, changing network condition is also a problem. Before and after migration, the routing of packets changes due to the difference of locations may happen. Services must not be interrupted before or after the migration. In summary, the following elements are required. Services should be dynamically allocated and migrated between different nodes without any packet loss or service downtime. Migration of FPGA applications should be just as possible as software. Now, we proposed an FPGA-based architecture that enables service migration. The proposed architecture maintains network consistency that does not affect other services by virtue of transparency and placing packets in order buffers at appropriate locations. The proposed architecture also reduces downtime for migration using the technique of service model prefetching, which starts a service at the destination node in advance. Additionally, state classification is introduced to reduce migration time and memory utilization. To describe the proposition in detail, I'd like to introduce the following terms: network transparency, network consistency, FPGA context, and state classification. It is assumed that the services deployed on an FPGA executes transparent processing, specifically IP-independent processing. By doing so, users do not have to update their settings about the location of target services and can access the services continuously. It is suitable for tiny IoT nodes because they cannot be updated due to their low cost and low power restrictions. Maintaining network consistency means that packets are lossless and their order is guaranteed during migration. It implies that there is no need to add any software or hardware functions about migration to client nodes or services. We utilize a packet buffer that stores network packets before and during migration in order to maintain network consistency. When there are no more packets on the migration path, the migration is performed. Packets are allowed to flow again by releasing the buffer, and the migration is completed. We define FPGA context as a concept combining logic and state components. The logic component contains the static circuits of services, which only mutate during the configuration of FPGAs. The state component contains temporary and dynamic values, such as the contents of flip-flops and block RAM. The logic and state components implement different migration procedures. The architecture has reconfigure partitions, RPs, and the migration logic component is equal to the moving of the contents of our reconfigure partitions. The logic component migrates by writing a partial bit stream of the service to the destination node. Service model prefetching, that means writing a partial bit stream in advance, is available in this case. Owing to the service model prefetching, the service can always run on the migration source or destination continuously. Migration of the state component is performed by using a scan chain. The scan chain is composed of flip-flops that store states to be saved and restored during migration. The contents of the chain can be replaced and observed externally by shifting the flip-flops. During migration, the state is read from the scan chain and transferred to the destination node through the network. The destination node then writes the received states to its own scan chain, and the states are maintained. The logic component stops operating during state migration because the contents of the scan chain cannot be accessed. This delay results in service downtime. Service applications are classified into three modes based on their behavior in network in order to reduce the amount of state migration. The types of states are determined by the properties of services and distinguished by 5 tuples, arrival times, and fin signals indicating the end of streams. The first is stateless mode. A stateless mode is a mode that operates independently between network packets. In stateless mode, services finish processing each packet and no state migration is required. The second is stream state mode. The stream state mode is a mode that has states for each network stream. When a network stream ends, its corresponding state also ends, meaning there is no need for state migration. Streams end when a fin signal is received or when a timeout occurs. The third is full state mode. The full state mode is a mode that contains states traversing multiple streams. State migration is always required in this case. The service provider determines which mode the service will operate in based on its behavior. This is the outline figure of a proposed architecture. The proposed architecture consists of FPGAs, CPUs connected to each FPGA, bitstream server, and migration controller. Each CPU is connected to the bitstream server and migration controller on a network. FPGAs are also connected to others. The migration controller manages and instructs CPUs. Partial bit streams are specific to each reconfigured partition. One partial bit stream cannot be written to different reconfigured partitions even for the same application services. So, bitstream server distributes partial bit streams based on the target services, target devices, and the target reconfigured partitions. CPUs perform partial reconfiguration after receiving partial bit streams from bitstream server. This figure shows migration for services in full state mode from FPGA 0 to FPGA 2. First, the source and destination nodes form a migration pair that receives a migration request. Second, the bitstream server distributes partial bit streams corresponding to the target reconfigurable partitions. Third, the migration destination executes service model prefetching. Fourth, to maintain network consistency, the buffer of the destination node begins buffering. Fifth, during buffering, set migration occurs. The states in reconfigurable partition 2 of FPGA 0 are read and saved. The saved states are then transferred through the network to FPGA 2. The transferred data are restored into reconfigurable partition 2 of FPGA 2. Sixth, the service at the source node terminates, and the service at the destination node starts. Finally, by releasing the buffer, packets begin to flow again. Next, I will explain the implementation. The NetFPGA Sume board was selected as a hardware-based computing node with 4 10 gigabit per second Ethernet ports. In the NetFPGA project, several reference designs have been distributed as open source, and you can easily test your implementation by incorporating your own design into them. In this implementation, the reference network interface card, NIC, was selected as a basic design because it can handle the line rate of network ports and contains a microblaze processor that works correctly. The proposed architecture was implemented between output port lookup module and VRAM output queues module. Since the reference NIC performs layer 2 switching, the proposed architecture does not need to consider the data link layer. This figure shows our implemented design on the FPGA. This design consists of static logic and reconfigurable partitions. Static logic contains the baseline of the proposed architecture and is not reconfigured. First, the stream controller distinguishes incoming streams based on their state and determines whether buffering is required. During buffering, streams are stored in the buffer module. The packets of incoming streams are routed to reconfigurable partitions, the ARP reply module, and the DMA0 module, which communicates with the microblaze processor. In this implementation, all packets are broadcasted over all of them, and each service decides whether or not to process the packets. Finally, the packets processed by each module are sequentially output from AXI stream switch. DMA0 is used for the transmission of state data, and DMA1 is used for access to the scan chains. We confirmed that the migration function by testing UDP echo server. In this figure, CPU 0 and CPU 1 are Intel NUCs. They were used for FPGA configuration. Client 0, Client 1, migration controller, and bitstream server are implemented as virtual machines on a workstation. The black solid line means connections over Ethernet. Migration from FPGA 0 to FPGA 1 was confirmed. First, the service of the UDP echo server is started on reconfigurable partition 0 of FPGA 0. It was confirmed that clients 0 and 1 can receive echoes. Second, the service migrates from reconfigurable partition 0 of FPGA 0 to reconfigurable partition 1 of FPGA 1. The bitstream server sends partial bit streams to CPU 0 and CPU 1, and the CPUs reconfigure the target reconfigurable partition of the connected to FPGAs. Following reconfiguration, we confirmed that client 0 can receive echoes, but client 1 cannot. This is evaluation of service downtime. In the case of the stateless mode and the stream state mode, only logic migration occurs. Logic migration uses the service model prefetching before starting a service at the migration destination. When prefetching is finished, the prefetched service is activated and the service at the migration source is terminated. Thus, the service downtime is virtually zero by performing the service model prefetching. In the case of the full state mode, both state migration and logic migration are required. During state migration, a service must stop to access the scan chain. Specifically, state migration induces a service downtime for scan chain access. In our implementation, this access requires 25 nanoseconds for each element in the chain for bytes, and 25 nanoseconds for every 64 bytes of Ethernet transmission and reception. The downtime can be represented as this formula by using a floor function when the number of the state element is n. The total throughput of our implementation was 40 gigabit per second because the data path length and frequency were 512 bits and 80 megahertz. To relax the timing constraints on services in a reconfigurable partition, the frequency was halved relative to that in the base design of the reference NIC. The total latency is the sum of the latencies of the service component and the architecture component. The latency of a service differs for their contents or properties. The latency of the architecture consists of the latency from the input port to a reconfigured partition, 177 nanoseconds, and from a reconfigured partition to the output port, 140 nanoseconds. This table shows the resource utilization of the static logic component of the target FPGA device. The static logic only owns 60% of the available resources because the reconfigured partitions account for 40% of the entire FPGA. The lookup table and flip-flop usage rates are 24% and 13%, which are marginal for implementing additional functions. However, lock RAM usage rate is as high as 57%. The block RAM was mainly used for stream controller, depicted as the red area, and for the memory of microblades, depicted as the blue area. This is the conclusion. We proposed an FPGA-based architecture that enables live migration between hardware-based computing environments on a network. The architecture maintains network consistency before and after migration by using state buffers and scan chains. The service downtime was reduced through service classification and stream management. The proposed architecture was implemented and evaluated in terms of service downtime, throughput, latency, and resource usage. The results demonstrate that live migration while maintaining network consistency in hardware is possible. The application range of hardware services can be expanded to flexible computing environments among cloud and edge nodes. That's all. Thank you for listening.